Hi everyone, welcome back to AWS Julie. Let's get started with our next lesson covering Domain 2, ML Model Development. In the last few lessons, we've talked about the first two steps of machine learning engineer lifecycle, to collect data and to process data. This domain covers the third step, which is to use the selected algorithm to train the model and to generate a model you can use to derive value. And the fourth step, which is to train the model. And for the well-architected machine learning lifecycle, this domain covers step 4, which is model development. Let's get started with logistic regression because the principles are used inside of machine learning. Logistic regression is a binary classification algorithm. So it's a yes or no, a 1 or 2, happy or sad, go or stop, sick or well, on and off, and so on. So I used to teach 5th graders how to snorkel. And after they completed their classes, we would take them on trips to Crystal River, Florida to snorkel with the manatees. Let's say that I want to collect data on how happy students are after their first snorkel experience with manatees. So I can use logistic regression to classify if students are happy or sad, or if they would go on another trip or not go on another trip with us, scuba syndrome. And I can plot the data collected on a linear line for our continuous set of data. And remember, for this whole course, I'm using very simple explanations, and this is a one-dimensional graph. If we use a two-dimensional graph, then the data might be represented this way. And on the y-axis is categorical data, and on the x-axis is continuous data. And you can use a curve to fit the data as best as possible. The curved line is called a sigmoid function. There is a threshold line, so if your data is above the threshold line, the distance away from 1 is it is happy, or the data that is below the threshold line is the distance away from 0 is sad. And the same for the x-axis values. Logistic regression makes a prediction or inference for each data point and creates two values. One is the distance from 0 or sad, and the other is the distance away from 1 or happy. And the probabilities are analyzed against the threshold. You can evaluate the values and see what the classification should be, which would be happy or sad. Let's move on to linear regression, which we covered under the fundamentals section. Remember, we walked through an example of how I would use the height of previous customers and the gear that was packed for their use, and then plot those historical data points on a graph. And once the data points are plotted on the graph, we can see a linear relationship between height and size of gear. And we can draw on this graph a line that represents a generalized linear relationship. And we can use this line to make predictions about new students or customers that sign up for a dive charter. It is important to understand that linear regression uses continuous data on both the x and y axis, and we also talked about continuous data in a previous lesson. And a linear regression with continuous data outputs a continuous model. Let's dive deeper into linear regression and talk about how we find the best line for our data to develop our model. We can measure the distance between the lines to see where the distance is the smallest, and this is called the residual sum of squares, or RSS, or the sum of squares residual, SSR. And we square the values to be a positive value. And this is an example of a loss function or a cost function. A loss function gives us the ability to evaluate the difference between predicted values and real values, which are our data points. And this is essential because the training of the model is to minimize the loss function, or the value that comes out of the loss function, to as low as possible. So from our earlier linear regression graph, we would produce another graph with the gradient on our x-axis and sum of squares on the y-axis. The gradient is the gradient of the model we are testing. We plot the data points against the current gradient. reduce the angle of our line, measure the sum of squares and plot again, and then change the angle again, measuring the sum of squares and plot on the graph with an X, and continue on to try to find the best fit for our model. And then you can see there is a relationship between these points. And at the bottom of the curve is the gradient we want because it represents the best fitting model for our data points. First, we can calculate all gradient values and calculate the sum of squares for all values. And this is a lot of work and data to process, and it's also a slow process. Well, we can use gradient descent, which is finding a random point on the graph to try to find the bottom of the dip and to find a slope that is level to 0 or flat. So at this point, we can see the gradient is steep and it goes over to the right-hand side of the graph. And at this point, gradient descent will step to the right and try again. And look at the gradient at this point, and we know that the gradient is still steep, but it's not as steep as it was. So it will try again and take a shorter step. It will check the gradient again and know that this is shallow and understands that this is approaching the minimum of the curve. And it might take another step and continues until it finds a slope that is 0 or is near to 0. And notice that it made 3 calculations to find the bottom of the graph. And this is faster than calculating all of the values. And it can go even faster with the statistical method or stochastic gradient descent or SGD. And the step size or learning rate can be set to tell it how fast you want it to find the bottom of the slope. You do not want to set the learning rate or step size too small or too large. And this takes a lot of experimenting and trying multiple values. The algorithm starts with a random point. You can also use SGD to figure out the intercept value, which is the value where the model will intercept the y-axis. Gradient descent is used in most machine learning algorithms. Let's move on and talk about support vector machines, which is a classification algorithm that is used to classify data that has more complex relationships. The algorithms we covered so far have been straightforward, and for example, logistic regression is not that useful on its own, but the principles are used in other algorithms. So let's talk about other algorithms for more complex relationships. This is a typical support vector machine graph. Let's go back to our earlier logistic regression example of determining whether students were happy or sad after their first snorkeling trip. And you can evaluate the values and see what the classification should be, which would be happy or sad. But what if we had more data and some of the sad students ended up on the far right side of the graph, and maybe they ended up here because manatees are large animals and they can be scary to snorkel with. I have seen adults scared, so it makes sense that children might also be scared to snorkel with the larger animals. And if we split it into the two-dimensional graph with happy students on the top and sad students on the bottom, we can try logistic regression with this data, but the sigmoid line just does not fit. Well, we can switch back to our single dimension graph because it is a one-dimensional data set, but we have a label of happy or sad. So we can add dimension to this data with a polynomial function with SVM. We're not trying to find more data from the data source. SVM adds an extra dimension as part of the statistical analysis of the data. We can add a polynomial function to the data, and that means that as we progress along the x-axis, we can take the largest data point to a polynomial function to the y-axis. So FVM or SVM adds dimensions to the data, spreads the data out, and finds a mathematical relationship between the data. This curve is called the kernel, a polynomial kernel for SVM. And we can draw a line from the extra dimension that splits the data apart and classify that data. and now there are data points above and below the line. This is called a support vector classifier. SVM applies more dimensions to find a mathematical relationship between the different data that you have, and you can see that for the most part, the happy students are below the line and the sad students are above the line. Machine learning is not exact, it's not perfect, so you can see some happy students and some sad students on the line too. And if we go back to the first graph, for our support vector machines, we can see the different classes of data. But in real machine learning, it is more difficult to see the class. But support vector machines can find the statistical split between the data set, and the points in our data sets are the vectors. The vectors that are in the center point, or the closest to the other vectors, are the support vectors. And these support vectors help to draw the lines. And the lines are the optimal hyperplane, which is not the midpoint between the center of the classes, but the midpoint of the support vectors. So the key is to find an optimal hyperplane that has the margin to separate out the two classes. Let's continue on and talk about decision trees, which are not an algorithm that you will use, but decision trees form parts of other algorithms. And this is an important step in understanding random forests. Decision trees look like an upside down tree. There is a binary decision point at the top, so a 1 or 0, a yes or no, true or false, and so on. If you get a true, then you come down one side, and a false would go down the other side. So we have a binary input, which could be, does someone like to scuba dive? And then we have a binary output. And you can also add in numeric inputs such as, does someone like scuba diving? Specifically, does someone like scuba diving and are over the age of 18? And this demonstrates a big part of understanding decision trees. This was a point of confusion for me back in 2019 when I started studying for the AWS Machine Learning Specialty Certification exam. Decision trees can deal with primary data and numeric data too, just like we've been talking about. When I was first studying and learning about decision trees, I saw this as decision trees, even with the numeric input, are still making binary choices or decisions with the question it has. So what would an example of that look like? Well, we could ask, if a person is older than 18 years old, do they dive twice a year or 6 times per year? And then our output is not a binary output like before, but a numeric output of 2 or 6. This is numeric, but we're still making a binary decision. But the way decision trees are built is that they decide where the cutoff point will be. And in addition, we can add more granularity by making it more complex with more features. So you can add in more steps. So maybe if you're older than 18, are you younger than 49? Well, then that is true. They dive more than 3 times a year. And as the numerous continuous data comes into the decision tree in the process of making the tree decide where the cutoff points will be. Trees are made out of nodes, and the root node has only arrows that come out of it. No arrows go into the root node. Internal nodes have arrows going into and out of them, and then the leaf nodes are at the bottom of the tree and only have arrows going into them. The root node is chosen from the feature that correlates best to our label. So if you choose a feature and build a tree and then continue on throughout the features, then you can compare and use all the trees built and determine which feature correlates and splits the data to best fit the label. One way to measure the relationship between the features and the target is to use the Gini impurity. The lower the Gini impurity, the better the correlation to the target data. And the smallest Gini impurity is used as the root node and then branches off that root node to true or false, but the true node also branches off. You stop when the branch becomes pure, or you get to the leaf node, or when the weighted average of the Gini impurity is greater than the previous Gini impurity node. Now, all of this is binary data, and I'm using this type of data because it's easier, but we can also use Gini impurity for determining the cutoff point for the continuous numeric data to find the cutoff for categorical ordinal data and to find the most significant nominal data. But when you add in new data, the likelihood of it working is low, so we need to put our decision trees inside of a forest. So let's look at a random forest and how we use decision trees to create random forests. And remember, we just said that decision trees do not generalize well, and you add in new data, the likelihood of it working is low. So we need to put our decision trees inside a forest. So how does that work? Well, we take random samples of our data. We also take random features of our data and then create mini trees. Then we ask the trees to vote on the predictions they want to make about the new data. Let's dive deeper into this process and start with taking random samples. So the first thing we need to do is to take random samples from our data through a process called bootstrapping. Bootstrapping is the process of taking random samples from our existing data set and creating a new data set. But we have the same number of samples in both data sets. And this bootstrap data will contain duplicates and missing samples. So we take random features from our data set to make our decision trees. So we are following the same decision trees from the last lesson, but we limited our data that is available to this process. So we take out the data and put that data back in. And then we remove different features. And in the real world, this process could be repeated hundreds of times to create hundreds of trees. Then we make our prediction by asking the trees to vote for their predictions. So we would have a new sample of data that is not classified and does not have a label as to whether they like scuba diving or not. And this data is passed into all of the trees created from the new data set and ask for their predictions. And then we calculate the most votes. And this is how classification works to determine if the new data added is for a person that loves scuba diving. Now remember, in this bootstrapping process, we left some of our data out, and that data was not used during the process of making the random forest. Internally, the algorithm uses that data to determine and report how well it thinks it has done in creating the random forest. The sample data that is not used in the bootstrap process is called out-of-bag dataset and is used to test the model. It uses samples that were never used to create the model to perform tests. Let's continue on with task 2.1, which is to choose a modeling approach. So remember, in our fundamentals lessons, we talked about different types of machine learning. Supervised learning is what we have been talking about so far in this course, where we have a data set that is already labeled, and we want our machine learning algorithm to learn from that. K-means clustering is an unsupervised machine learning algorithm where the data set is not labeled, and we want the machine learning algorithm to find a pattern in that data. K-means clustering is an unsupervised algorithm that we use when we want to cluster the data in a way that we as humans cannot see. We are asking the algorithm to cluster the data for us. So how does K-means algorithm figure out the set of clusters in the data? Well, the first step is deciding K. So how many clusters do we want to find? K is the number of clusters we want. So let's set K equals to 3. And I added different colors to each cluster to visualize this better, but again, in the real world, these clusters might be hard to identify. And the K-means clustering algorithm will not know the colors or be able to cluster these data points when it begins. The second step the algorithm will do is to randomly assign a sample point to be the candidate for the center of the cluster. So it chooses 3 samples and it makes each one a different color. And all these points will be, the current center of the cluster. So let's add X for the random start point. The third thing the algorithm will do is to go through each data sample it has and determine the nearest cluster. So it will take a random point and measure the distance between each colored point to see which distance is the shortest. And then the shortest distance or line will be the current classification to that point. So that makes this data point, the light blue X, will belong to this cluster, which is the nude colored cluster, and then the algorithm moves on. Then the algorithm will recenter the cluster based on the center of the points within the cluster. And it might not be well defined, so it will go back to step 3 and examine each data point to determine the nearest cluster. It will choose a new center, and then the algorithm goes back to step 3 and does it all again until it reaches a balance and nothing changes. No center points change. But it does not always work out well, so you can end up with clusters that don't make sense. So how does k-mean clustering ensure its outputs are the best? Well, it looks at variations and measures the total variations by looking at the center of the clusters it has found and the members of those clusters. So for the first cluster, it measures from the center of the clusters out to all of its members. Then it adds up the total distance and looks for the least variation or the smallest distance, and then that is the model to use. And you may be asking, well, Julie, how do we choose a good value for k to start with? Well, again, the answer is total variation. So here's a question. Do you also want the least variation again? No, because as you increase the value of k, the variance will come down until k equals the number of data points you have, and this is not clustering. So the algorithm graphs the number of variations against the number for k to identify where the reduction in variation starts to drop off. And the algorithm is looking for the knee of the graph, which is the point where increasing k has less impact on the reduction in variation. K nearest neighbor is another supervised classification algorithm. So let's go back to our data set for our k-means discussion. K for k nearest neighbors means something different than what k means or meant for the k-means algorithm. So let's add a new data point for this data set and ask how to classify this new data point. Well, you might be thinking, what is the class of the nearest neighbor to this point? Well, let's say that the nearest point is the light blue data point. So should this also be classified as light blue? Well, for k nearest neighbors, k is the number of neighbors that need to be taken into account when classifying and adding new data points. So if you choose 3, or k equals 3, then that means the algorithm needs to find the 3 nearest neighbors, tally that up, and see which is the predominant class. And in this case, it is the dark blue. So this new data point would be classified as dark blue. But how do you choose a value for k? Well, it's just experimenting, and again, be cautious, because if k gets too high and near to the number of samples in a class, and this algorithm can be useful with multidimensional data and can also be used with other algorithms. For example, you could use k-means to classify data points and then use the k nearest neighbors to make inference of that data. Let's continue talking about algorithms, and let's talk about latent direct allocation. It is a machine learning algorithm used for topic analysis within a collection of documents. But let's pause for fundamentals and define what a document is for latent direct allocation, or LDA. Most of us think of a document with text words on it, such as the images on this slide. So it's a sheet of paper with text that conveys a message. But remember from an earlier lesson, when we're talking about contextual data, there are processes we apply for machine learning to better understand a text document. But LDA does not look at the document in the same way that we do. It needs to use techniques that we talked about earlier on. So it has individualized token words from the sentences and documents. There is no sentence structure. It's just a collection of words. And quick check, do you remember what we called this? We called this a bag of words. And if you look at the collection of words, you can probably figure out the topic, but you might lose the meaning. And LDA needs more than one document to perform topic analysis. And when we have more than one document, it's called a corpus of documents. And each document in the corpus will have a different topic or mixture of topics. So let's dive deeper. A topic is a frequency distribution of words. So if we look at these two topics, you can see we are counting the frequency of the occurrence of the words. And are you able to visualize the word that appears the most? Well, these graphs show the frequency distribution of the same set of words across two topics. So topic A is probably scuba diving, and topic B is probably machine learning. But it's important to understand that the LDA algorithm does not define what the topic is about. It defines that topic as a distribution of words. So the topics are not labeled with values. It just defines that we have two topics. So when you use LDA, you give the algorithm a corpus of documents and ask it to find a certain number of topics. LDA sets up a process for how a document is created because it says a document is a distribution of topics and a topic is a distribution of words, and it uses statistical analysis to navigate back and forth on this line. And the words are multiplied through the distribution of the topic or topics to create a document. Now, this is not natural language processing. It does not create a document that we can read. It just creates a document such as the one we defined earlier, a bag of words, and the words relate to a certain topic. So LDA will get words from all of the documents from the corpus of documents and create a large bag of words. Then it takes the words and assigns topics to the words, which are initially randomized topics applied to all of the words. Then it starts an iterative process to calculate the documents to a topic distribution and the topics to words distribution. And then with the tallies it has, it will use the LDA process to go back through and reassign those topics and then continue this loop until there is a point of convergence that's found with a predominant topic for a document and a predominant set of words for a topic. It uses Dirichlet, I'm not sure how you pronounce it, distribution, and gets very complicated. But for this exam, we are focusing on the applied level and how we can control LDA and choose the number of topics to analyze and process the data to ensure better data quality and then run that data through the training to create the model. Let's move on and talk about principal component analysis. We mentioned PCA in an earlier lesson. It is an unsupervised algorithm and is used for dimensionality reduction and used as a pre-processing step for the other machine learning steps. But back to our fundamentals. What is dimensionality reduction? Well, let's look at this picture of a manatee. My dad bought this candle for me as a souvenir after my first snorkeling trip with the manatees. So it's pretty old. But looking at this picture of a manatee, what do you see? What information and attributes can you extract out of this object? Well, it has a height, a width, a depth, it's gray, it's textured, it has a pink bow, and purple and white and maroon flowers. So fundamentally, how are you doing this? Well, we're looking at this image of a manatee on our laptop, tablet, or phone. So it's a two-dimensional screen. But in fact, you're looking at a two-dimensional array or value. But you still infer or see the information about this manatee-shaped candle. All of the dimensions are reduced down to a two-dimensional array of single-digit numbers. And this is PCA, or Principal Component Analysis. It takes a multidimensional data set and reduces it down to the principal components. You can still see and understand the data without having all of the data, but this is not to do with the image manipulation or image recognition. PCA is taking a lot of dimensions of data and compressing that data down to just the principal components. So let's look at this on a graph. We're starting off with a two-dimensional data set, and we need to get it down to a one-dimensional data set. And on our graph, we have an x-axis and a y-axis with our data points spread across the two axes. So how does this work? Well, if we get rid of one of the axes, it reduces everything down to one axis. So let's get rid of the y-axis, and you will see everything is reduced down to the x-axis. But in doing this, we lose a lot of the y data, and we don't want to do that. So the algorithm can use the minimum bounding box to draw a box as close to possible to the data points in this orientation. And it will analyze the data points from different points of view to get the box as small as possible. So it may rotate the box. And when it does this, the axis is changed from the original data set to principal component 1 and principal component 2. Now, we have not reduced the dimensionality of our data at this point because we still have 2 dimensions, but the algorithm has analyzed the data set for the principal components. So let's pause for fundamentals and ask, what is PC1? Well, PC1 is where there is the largest spread of data along the x-axis, or along the axis. It is the component of the data that influences the points to the greatest, and the PC2 is the second influence on the data, so it has less influence than PC1. Now at this point, the algorithm will remove PC2 and consolidate the data points down to PC1. This is not the same as when we remove the data on the y-axis. This data contains both information about X and Y, and that was captured by its principal component. So let's look at going from 3 dimensions to 2. At this point, the algorithm does not use a box around the data points. It uses a cuboid because it's 3-dimensional. It will again find the longest side for PC1, the next longest side for PC2, and then the shortest size for PC3. And this cuboid is not parallel with any of the axes. It's just a floating shape and binding the data points together. And to conduct dimensionality reduction and remove a principal component, the algorithm changes its perspective on the data points, and in doing this removes PC3. And now there is a 2-dimensional graph that represents the data. And again, instead of having axes X, Y, and Z, we now have PC1 and PC2. When PCA is performed, we are not removing the features. We are remapping the entire data set down to its core or principal components, and then choosing how many principal components we want to include in our output data set. So why do we do this, and what is a use case? One example is when you have a large data set of patient data and you're inputting this data into a random forest classifier. Sometimes there's a whole section of features that have high correlation with each other. And if we pass that data into a random forest classifier, then the classifier will have to go through each data point and features, measuring each one and seeing where the threshold cutoff should be, and mapping it out to different branches of the tree. And this is a lot of work for just a little bit of benefit. And here, PCA is a type of feature engineering where the data can be transformed into a smaller data set while maintaining the principal components of the original data set. And it's important to understand that all of the data that is mapped to in the new data set is a different data set with principal components rather than the original features. And when it is mapped to a label, the work is reduced for the random forest classifier. So PCA maintains what is important about the data, but makes it smaller with richer data to pass along the algorithm to build a model to use for inference. And this is an example of model chaining, where we can use multiple machine learning models in a sequence to process data and create a model and make inference about new data. And this is a great time to remind y'all that I'm adding as much as possible to this course, but machine learning is a huge topic, and we're currently trying to focus that machine learning and all of the information and knowledge and algorithms, everything about machine learning to the associate level machine learning engineer exam. So let's pause again and go back to fundamentals, and let's talk about neural networks. What are neural networks? Well, they are a basis of deep learning. So we have machine learning and then neural networks and the deep learning, which is a subset of machine learning. So when we look at a neural network, we will see images that look like this. Let's pause for fundamentals again and look at deep learning in the brain. And in our brain, we have networks of neurons, and small electrical charges get passed through the network of neurons for decisions and thoughts and memories and so on. And the neurons have inputs and outputs and processes and stuff inside that make it all work. And when these are all strung together, we have consciousness, thoughts, feelings, memories, and ideas. And in machine learning, we have artificial neurons, which have similar components. So again, we have inputs, outputs, and processes inside that make it work. And the processes or stuff that makes an artificial neuron work is memory with functions and values inside of the memory. And in deep learning, you will see them represented similar to this image with lots of artificial neurons together, and they're all connected. And you can see in this image multiple layers. So how do we use these neural networks to make inference and predictions? Well, if we go back to our example and create a table of data with labels for our manatee and fish. But for this example, let's also add in images of shark. And let's say that we already have this information labeled. So how do we get a pre-trained neural network to make its predictions on different rows for the data in this table? Well, the way that it works is that the three features are passed into the neural network. And this is the input layer. So the features go in parallel to the first layer of the network. Then through the connections and other nodes in the network, calculations are made. And then on the right side, one of the neurons has a value in it that is higher than the others, and that is the prediction. Another example for neural networks is image recognition, and this works the same. Remember, an image is a large table of data made up of pixels. And the algorithm applies each different color value of the pixels into the input layer of the neural network. And remember, this is a trained network, so it is trying to figure out if we're looking at a picture of a fish, manatee, or shark. So the input layer is a collection of neurons that take the data from our data set. And the output layer is where we get the predictions. And the design of these two layers are important to ensure that we get right. So the networks in between are all more layers, and there can be multiple layers of many different sizes, and they are called hidden layers. And this is trial and error to determine what types of sizes output the best predictions. And they can get larger with multiple input nodes, output nodes, and connections. But let's go ahead and move on. So far in this course, we've talked about basic neural networks using the activation functions inside individual neurons with activations, biases, and weights. This is the general structure of neural networks. But modern neural networks use more sophisticated layers inside of the networks and introduce different layer types. So let's talk about convolutional neural networks, or CNN. What is CNN? Well, it's a neural network with convolutional layers and is mostly used for image classification. And these CNNs are great for classifying images with a higher resolution. For example, the MNIST handwritten data set is not a high-resolution image, and it was easier to build a neural network that could take all of the pixels and do calculations throughout the network to get the classifications. So remember from an earlier lesson, we have an image of a neural network and images of a manatee-shaped candle Well, this is an image that has a higher resolution, big dimensionality, lots of pixels because of the higher resolution, but it also has different colors. And if you pass this information or data set into the previous neural network pictured on the right, the neural network will have a hard time, and the neural network will need to be enormous to deal with this quantity of pixels and data. But inside the hidden layers, we can use convolutional layers inside the network, and we might introduce more layers. And convolutional layers to detect parts of the image can be specifically designed to look for certain aspects of the images, such as edges of an object or loops. And inside the neurons for the convolutional layers, there is a filter or a kernel. And this is a learned element of the model, and it goes through the training processes and finds the filters. The learned filters or kernel activate for spatial features that correspond to the classification of the data. Let's continue talking about neural networks, but focus on recurrent neural networks, or RNN, which is a different type of architecture for neural networks. RNN are used for sequenced or time-based inputs. With convolutional neural networks, we passed in images as the input to classify fish, shark, or manatee. But for recurrent neural networks, you might pass in a sentence, and each word is passed in 3 times. Or passed in separately, I should say. And the difference here is that each time the data is passed into the neural network, it is not looked at as individual data and that has no context. And the neural network does not know these words are inside of a sentence or have a relationship with the words that came after it or before it. But the recurrent neural networks pass output from the neural network back in as input. So it has different patterns set up than a convolutional neural network. So as you pass in the first part, it might get an output, but it passes that output back into the neural network. And since this first part of the sentence was passed back into the neural network, the first 2 words are looked at in context. And then when the third word is passed into the network with the first 2, all of the words are looked at in context. So what is a use case for recurrent neural networks? Well, RNNs are great at translation because some languages with the different dialects have words in different order to each other. And having the order of the words in the context of the sentence it is in is important for translation, audio analysis, sentiment analysis, and time series data analysis. RNNs have a hidden state, which is maintained by the RNN as it's making inferences as the data arrives into the input. It maintains this state and maintains this knowledge of inputs it has previously received. One important thing to consider is that the final hidden value in our network, one word might be weighted more than the first 2 words in our sentence. So I love manatees, and you can see that manatee has more weight than I in love. And this is an example of the vanishing gradient problem, which states that the larger the neural network, the less impact gradient descent has as it traverses through backpropagation from the final output of the network all the way back to the beginning. And the changes in the gradients in the last few layers in the network will be more drastic than the first few layers of the network. In a large neural network, the gradient will essentially vanish by the time it gets to the beginning of the network. So early stages in the network do little during backpropagation, and the first sample has less impact on the calculation or overall prediction. And the first part of the sentence might have been important and changed the meaning of the sentence. So what is our solution to help mitigate the vanishing gradient the vanishing gate problem? Well, there is long short-term memory, or LTSM, which is a type of RNN. LTSM uses gates to be able to determine what is important and should be remembered, but also what it should forget. It introduces multiple neural networks inside of the LTSM node, inside of the neural network. And this does add time to train because there are multiple neural networks at all stages along the process. And if you don't have extra time needed to train, then you can use a gated recurrent units, or GRU, which is another type of RNN and also uses gates, but is structured differently. It's not as complicated, and it uses less processing than an LTSM, and it may be faster to train. Okay, let's continue on and talk about word-to-vec, which is a method to create word embeddings, which is often used at the beginning of natural language processing set of algorithms. But let's ask a fundamental question. What is word-to-vec or worded embeddings? We've talked about text encoding and how we can create a bag of words for this. But when you do that, you lose all context of the sentence because it's just a bag of words. A bag of words is great for statistical analysis of words in a document, but it does not provide the context or syntax to give you the ability to understand the sentence. And the way to understand the context in the sentence is to look at the word and the words on either side of that word. And as we scroll across using a window of context, word-to-vec tries to create a model that represents the context that a word sits within. And there are two methods to do this. The first is a continuous bag of word, which predicts the target word based on the surrounding words. As the context window is slid over the document, it becomes a small bag of words. The order is not important, but it is continuous because it continues to slide over the document. And by subbing the words together, it will make it equal to the output word. So this method does not scale well, but there's also another method called skipgram. Skipgram tries to predict the context from a given word, and in this method, all of the words in the document have a number associated with. Word-to-vec takes a word and converts it into a vector, which is a list of numbers. And this method equals the relationship to the words. The vector that represents the word uniquely identifies the word within a bag, but because it has a relationship to the context that the word came from, the algorithm can use that to represent the relationships between different words. And this method equals the relationship to other words. The vector that represents the word uniquely identifies the word within a bag, but because it has a relationship to the context that the word came from, the algorithm can use that to represent the relationship between different words. Let's wrap up this algorithm section and talk about sequence to sequence or sec to sec, which is not an actual algorithm, but a pattern of algorithms for a specific job. We've talked about natural language processing and recurrent neural networks and long short-term memory networks. So if we go back to our earlier sentence from our text data lesson, you can use sec to sec to translate sentences into a completely different language. So we have this quote, "We are not greater than other animals, but should take the responsibility to look out for them. Show compassion, show a kind form of coexistence, lend a hand to conservation efforts." And Ocean Ramsey said that. It's one of my favorite quotes. But sec to sec can translate this to another language. And from a machine learning point of view, we've talked about machine learning models of linear type, deep learning type, machine learning type, and so on. So we understand how most of these models work with an input that is pushed through, and then you get an output. But for this type, we have a sentence that we are inputting into the model, and our sentences have different lengths in the different languages. And for the output, we will have different lengths for the different input sentences, but it's also a different length from the original input sentence. So in this example, the input sentence has 33 words, but the output sentence has 30 words. And recurrent and reconcurrent neural networks can deal with these differences. But you cannot use just one. The way it works is you take the input sentence and pass it into a layer in an encoder LSTM. And then the state is passed into the recurrent neural network over and over again as it sequentially passes in all of the words from the input sentence. And each time you add in a new word, you also get some state that is passed to each step, and that state represents the words that have come before. And at the end is an output that represents the input sentence. The neural network and LSTM encoder encodes the sentence into the output. So the LSTM has been able to accept the input at a variable length, but how do you get the output as a variable length? At the moment, we only have one encoded output vector. Well, the next output vector is duplicated a number of times, and that number of times is learned by the system. And the cloned output is then passed into the second LTMS, which is called the decoder LTMS, and then you check each individual output stage of the LTSM to get each of the words translated. And the final output, it will have the finished translated sentence. The important thing to remember is that sec-to-sec is great for translations because the encoder and decoder work together to accept variable length input and produce a variable length output. So the name comes from a sequence that goes to another sequence. What are other applications or use cases for sec-to-sec? Well, besides translation, another use case is image captioning with mathematical data that needs to be translated into variable length output of words. So it takes an image of a manatee in the ocean and it can output a sentence as a manatee in an ocean. So how do you consider interpretability during model selection or algorithm selection? The higher the interpretability of a machine learning model, the easier it is to comprehend the model's prediction. But there is a trade-off to be considered between what the model has predicted, which is the model performance, and why the model has made such a prediction, which is the model interpretability. And there are methods for model interpretability that can be classified into intrinsic analysis and post hoc analysis. Intrinsic analysis can be applied to interpret models that have low complexity or simple relationships between the input variables and the predictions. The simple relationship between the inputs, input variables, output results, and the predictions in high model interpretability can lead to lower model performance because the algorithms are unable to capture complex nonlinear interactions. These models are based on algorithms such as linear regression, where the prediction is the weighted sum of the inputs, and decision trees, where the prediction is based on a set of if-then rules. Post hoc analysis can be applied to interpret simple relationship models and more complex models such as neural networks, which have the ability to capture nonlinear interactions. These methods are often model agnostics and provide mechanisms to interpret a trained model based on the inputs and output predictions. Post hoc analysis can be performed at a local level and zoom in on a single data point, or at a global level and zoom out and view the overall behavior of the model. If you need to improve the model performance, AWS recommends increasing the model complexity and using post hoc analysis methods to interpret your results. So let's wrap up task 2.1 from domain 2. And for your exam, ensure you understand the AWS services for this exam at the appropriate level, which is the associate level for this exam. And let's step back to our fundamentals and talk about the AWS machine learning stack. So remember, on the bottom of the stack, there is the infrastructure and machine learning frameworks, such as Amazon EC2 instances, Amazon Machine Images or AMIs, GPUs, containers, and more. Everything is built on top of this infrastructure layer. Then on top of the infrastructure layer is the AWS machine learning services that we're going to talk about throughout this course and in just a few minutes. And these are all pre-built models already trained by AWS, and you can use these services and integrate them into your application. And for the exam, make sure you understand the AWS AI services as well. So Amazon Lex is a chatbot engine and is a service that powers Alexa. And so for your exam, make sure you understand what it is, what it does, and use cases. Amazon Polly is a text-to-speech service that supports using the speech synthesis markup language, or SSML, and you can choose how you want your speech to be rendered, such as shouting or whispering. It also supports custom lexicons, which you can use to explain how words are pronounced. So make sure you understand what that is, Amazon Polly is as well. Amazon Text Track and Amazon Comprehend are both text-based services powered by machine learning, and you can use these services through an API. Amazon Text Track extracts text from images and is an example of optimal character recognition, or OCR, and it grabs the meaning out of documents and can work with both printed characters and handwriting. Make sure you understand use cases for Text Track too. Amazon Comprehend is a natural language processing tool. The use cases are language detection and extraction of things from text, such as key phrases, places, people, events, brands, and so on. Amazon Transcribe and Amazon Translate are text-based services. So Amazon Transcribe is a speech-to-text service, and it is the reverse of Amazon Polly. Amazon Translate is a service that translates text files, and it includes 71 languages. It might include more now, but when I was building this course, it was 71. But it also includes bidirectional translations too, and it uses neural machine translation. Amazon Recognition is a machine learning service to analyze images and videos that is pre-built and pre-trained, and there are different services that you'll need to understand for the exam under Amazon Recognition. Amazon Personalize is a personalized recommendation service. The use cases are recommending items that other customers bought, similar items, sharing promotions and notifications. And for this service, you need to bring your own data, your own customer information with a list of items that have been purchased in the past. And to wrap up our coverage of AWS AI services, let's talk about Amazon Bedrock. Amazon Bedrock is a fully managed service to build generative AI applications on AWS with foundation models and tools to customize. And you can use different foundation models that are best suited for your use case. And let's also talk about Amazon SageMaker, which is in the machine learning services layer of our stack. Amazon SageMaker can be broken down into even more layers, or a SageMaker stack. And a user can use the AWS console, SageMaker notebooks, and more to interact with the SageMaker user interface. And there are also multiple AWS SDKs for multiple different languages. And remember that Amazon SageMaker has its own specific SDK for Python. And then for the infrastructure level, there is an infrastructure layer that we discussed earlier, but on top of that infrastructure is a Docker container infrastructure. And remember that these containers are run to support machine learning workloads. And you can use your own containers or containers created by AWS. And these have built-in algorithms. These built-in algorithms are real algorithms created by scientists, and AWS takes these existing algorithms and creates versions of those that work in SageMaker. And then SageMaker takes the algorithms and containers in SageMaker and manages all of that orchestration. So for the exam, ensure you understand the Amazon SageMaker built-in algorithms that you can use to solve your real-world problems. And what helped me understand and remember these algorithms when I was starting out was grouping them by data input format, how they take the data and what data they take. And the three groups are tabular, text, and images. Tabular algorithms take tables of data, such as patient records or customer records, so numerical tables of data. Text algorithms take documents and use natural language processing, and image algorithms are where the input is an image. But let's tie in all of this content so far that we've talked about. We know that machine learning can help us accomplish empirical tasks that require some sort of inductive inference. This task involves induction as it uses data to train algorithms to make generalizable inferences. This means that the algorithms can make statistically reliable predictions or decisions or complete other tasks when applied to new data that was not used to train them. Amazon SageMaker helps to select the best algorithm for your task, and the tasks are classified on various levels of abstraction. At the highest level of abstraction, machine learning attempts to find patterns or relationships between features or less structured items, such as text in a data set. Pattern recognition techniques can be classified into distinct machine learning paradigms, each of which address specific problem types. And under the fundamental sections, we talked about the three basic paradigms for machine learning that are used to address various problem types: supervised learning, unsupervised learning, and reinforcement learning. The types of problems that each learning paradigm can address are identified by considering the inferences or predictions, decisions, or other tasks you want to make from the type of data that you have or could collect. Machine learning paradigms use algorithmic methods to address their various problem types. These algorithms provide recipes for solving these problems. However, many algorithms, such as neural networks, can be deployed with different learning paradigms and on different types of problems. Multiple algorithms can also address a specific problem type, and we've talked about that throughout this course. Some algorithms are more generally applicable, and others are quite specific for the problem type. So the mapping between machine learning algorithms and problem types is many to many. Also, there are various implementation options available for algorithms. So long story short, for the exam, make sure you dive deep into Amazon SageMaker and the AWS AI services. I'm going to wrap up this lesson, and this covers Domain 2 Task Statement 2.1. And in the next video lesson, we will cover Domain 2 Task Statement 2.2, which is to train and refine models.